Avoiding a training wreck. Metrics are used for the successive refinement of a solution to a problem. So we have this train, validate cycle, and metrics are applied at each iteration to identify issues that we have at each point in the solution process. So measures or metrics are applied to test sets. They allow us to reject poorly performing algorithms because one of the curses that we run into is that algorithms always produce results. The extreme positive, totally positive, totally negative, and extreme random and coin toss classifiers, you always get results. They're not very good, but you always get them. So metrics have to guide us in rejecting poor performers. We have to differentiate, therefore, between making an algorithm work and measuring an algorithm's performance. And our emphasis here is on the latter. We need to assess and improve algorithms. We don't want to get trapped into using global statistics like accuracy and mean error because they don't help us refine our solutions. We need metrics that can target specific weaknesses. So remember Polya's method? We got to where we had metrics to interpret models, and that leads us to a better understanding and successive refinement of solutions. And that means we can now do this entire process, successively refining. So how do we do that? Well, train, validate, test, repeat. So for a sequence of training sets, we partition into training and validation. We train with a given set of parameter values, test on a validation set for those parameter values, and then use a metric to score the algorithm with those parameters. And then we can find the parameters that give us the best scores with respect to those metrics. Then we'll test on a sequence of testing data sets and use the metrics to assess the overall solution itself. And then we repeat. So ideally we would have new data sets for every single step, but it's very rare to have multiple training and testing sets. So for example, often the test set itself is a gold standard, something that's known to somebody, like organizers of a competition that assesses solutions. So we don't have multiple sets, and that's going to bring us to the desire to use what's known as cross-validation. So cross-validation means we partition these usually very large data sets into several different partitions. N-fold cross-validation means you partition the test set into n subsets. And in each of n iterations, therefore, the ith partition is used as the testing set, and the other partitions are used to train. This simulates having many different independent data sets. So for instance, let's look at the issue of overfitting. An algorithm may be so closely fit to the training data, it cannot accurately predict the test data. So let's look at, for example, what overfitting by a regressor would look like. So suppose we have some data, and we have a test set. If we were to fit a curve through every single point, we would get fairly awful predictions for the test set. Similarly for a classifier, if we overfit, especially if we overfit to the positives or overfit to the negatives, then we can end up with very poor accuracy on a test set. Cross-validation is a great tool for revealing overfitting. So for instance, here we have the first fold of some n-fold cross-validation, and in the second fold is the same data, but it's a different test set. That means we do the same process again, look at the test set, and we get predictions, and again they're fairly horrible. In fact, cross-validation has showed us that the differencing in the training sets leads to wildly different models and large errors in predictions. Therefore, we might be moved to take a higher bias model, one where we have smaller errors on average and more stability from one fold to the next of a cross-validation. So let's look at this actual versus predicted. Actual responses are y sub i's, where y sub I is the true function plus some noise. Predicted responses come from the fit, the best fit to the data from the model, the best fit to the training data. So therefore, after we've trained an algorithm, the testing process yields a sequence of actual y sub i's and predicted values of those y sub i's, y hats. So therefore, if we put these as pairs, the y sub I hat should be close to the line actual equals predicted. So if we plot these as points, it should be close to this line. And ideally, the total squared error should be small. Now remember the law of large numbers? Well, in our case, it says that if y hat is the fit applied to a variable x, then that's a prediction of an actual y in a test set. The expected squared error, the expected value of y minus the f hat of x, that's the expected value of the total squared error over, we would imagine, an infinite sequence of tests. Now for a single test set, we actually would get an approximation, the error sub n, and that's the sum of the differences between the y sub i's and the f hat applied to the x sub i's squared. And for large n, that might be an approximation to the actual error, but remember the actual error is an expected value over and what we would imagine to be an infinite sequence of tests. So in general, we want to approximate the expected value of y minus f hat of x squared using multiple test sets, in other words, cross-validation. So let's look at an example, simulated grade data. So suppose we want to predict a final exam score, exam 5, from the first 4 exams. The test set is actually the first 4 exam scores before the final. This is actually ideally what we would collect during the semester, and then before the final exam we would predict their final exam score, and we would know which students need some kind of intervention before the final. So we're only going to look at the training set. The test set occurs in the real world when the model's actually used. We'll have 500 observations. Here are the exam averages. Notice exam 5 averages significantly lower than the others. So we're going to drop the pass variable feature because it actually is based on whether or not the average of the 5 exams is higher or lower than 70%. So here we see the code to do this in Python. And there's our training set, the 4 exams. And then we'll do some kind of k nearest neighbor regression. We'll train it on the training sets and we'll test it on the x VLD, y VLD, because we're actually going to be validating, get the best parameter. What's the best k, for instance? So here you can actually see that process. Here we have the data. Notice I've got the predicted versus the actual. They should all lie on the line actual equals predicted, but they don't. How close are they? Well, we can use correlation. Correlation is the predicted slope, the slope of the line predicted by the y sub I hat. In this case, it's 0.88. Ideally, it would be 1. The r squared coefficient of determination, that's the proportion of the variance in the dependent variable predicted by the independent variable. In this case, it's 0.753. But notice that we're using a 1 nearest neighbor here. That's the most complex model you can use with k nearest neighbors. Are we seeing overfitting? Is this the best k? Should we be using cosine similarity? The default is distance, not cosine. Should every neighbor have the equal weight in the prediction? So the prediction is essentially the average over the neighbors, but should we weight those averages based on how far a neighbor is? So we're going to answer these questions using a grid search cross-validation. So this is going to be a cross-validation for each combination of parameter values in a grid parameters dictionary. Nearest neighbor's regressor, tenfold cross-variance for each parameter combination, coefficient of determination used for the scoring. So here we see that we're doing 840 of these actually, and we're getting some messages. So took 3.5 seconds. Looks like the best metric is going to be Euclidean, so we are not using the cosine. The best nearest neighbor's parameter is 3, and we should use distance weighting for the averages instead of just every neighbor having the same contribution. The best score here is 0.6166. But R2 is not the best metric for determining if we are overfitting. So let's recall the bias variance trade-off. Error is the square of the bias plus the variance plus irreducible error. Bias decreases as model complexity increases, variance increases as model complexity increases. This is applied to the validation set, and our goal is parameters for which the model has minimum error. So we'd like to use error as some kind of measurement. Distances can lead to kernels, but variance and error are not distances, so we don't get similarities. Ideally, we'd like something like k of x y hat is 1 minus in this expression, but instead we use something closely related. We use what's called the explained variance of y comma y hat, and it's the variance of the difference in y and y hat over the variance of y subtracted from 1. Notice it's not symmetric. It's less than or equal to 1. The best score is 1, but it's not a similarity kernel again because it's not symmetric. If we go back to our example, we'll use the grid search now with cross-validation based on explained variance. Now there are other metrics similar to error and similar to explained variance score. So remember, every application is unique. We're not suggesting that any metric is always the right one to use. So here is our grid search again. We're using explained variance score for our scoring. And here we have a correlation of 0.89 and an R squared of 0.786. And what does this mean? Well, it means we finished this cycle. If we wanted to get better, probably going to have to use something besides nearest neighbors. Or we're going to have to use more data. So typically more data leads to results much faster than does better algorithm. So if you have to choose between more data or model based on more sophisticated algorithm, we'll tend to go with more data. More data is often why we select a different algorithm. And it also shows a big problem with nearest neighbors. If we use small k, then we're only using small parts of the data sets for each prediction. So we may have a massive data set, but we're not using all of it for each prediction. But large K means we begin approaching these global statistical measures where we're getting essentially just the average over everything if practically everything's a neighbor, for instance. So in summary, without cross-validation based polio type approach, overfitting is an issue, parameters wouldn't be optimal, bias is unknown, variance is out of control. But when we use cross-validation and a polio type problem-solving approach, metrics can be used to select best parameter values, and we can do successive refinement and get better and better models. And often better means more data.